the slides here, and then whenever we need it, we can refer to the equations. Like so, for example, here we consider a shaft with the cross sections. It's kind of L shape. The thickness is uniform. T equal to 0.002 meters. And say, for example, here we given the dimension, this is 20 millimeter, and this is 50. And this is 20. And on the top is 50. So for this case, the allowable shin stress is 3 MPa. And we want to find the first one is the maximum torque. That can be allowed to apply to the shaft. Okay, so we try this one first. So basically this is the thin wall material is looking like this. So for this case, we can apply is this formula. The tau equal to T over 2TA, and T is the thickness, and A is the area, and again the area enclosed by the center line through the wall. So from here, we simply plug into this formula: T equal to tau. Tau equal to T over 2TA. And this one must be less than or equal to the allowable stress. So for this case, we can see T equal to 0.002 meters. And A is the area that is enclosed by this line. So this is A. And you can plug in the information. A should be easily calculated. That one is equal to 1404 times 10 to the minus 6 meter square. So therefore we have all the things here. So therefore T must be less than or equal to the tau allowable, multiply with 2 times T times A. So from this calculation, we can quickly calculate 16.85 Newton meter.
Jesus.
That's goodness. And then the follow-up with those informations, then we might be interested, say, for example, using the same formulas, we can exercise, say, for example, to find. So if we are given using the maximum T, so say if we using the T equal to 16.85 Newton meters. Then we want to find the angle twist per length. This is a cross section, and then the protruded that it gave us the length. We didn't specify the length, so here we can see how can we calculate these questions. So basically, this to calculate the angle of the twist for related information, basically we utilize this equation. Okay, so let me get rid of this. In that equation, you can see we have to deal with this kind of integrations, and we see how can we do it. The angle of the twist is d, and the angle of twist per unit length. So that means d divided by L, and this one is defined by beta. Okay, so basically this one we're looking for is looking for beta. Okay. So once we have the beta, then really depends on how long the length you like to use, and you simply multiply with that length, then you will get the angle of the twist. So for this case, we plug into here, that will be equal to t divided by 4g the a square, and then integration ds over t. Okay, and so for this case, you can see this one can be quickly done. Is we know the t, and we know the a. The a is we calculated here, and g is the rigidity. So for example, here I give say the g equal to 30 GPa. So basically here all the information has been fixed. So for this exercise, we can try to see how can we implement this one. So here is 4, let me rewrite this coefficient g a squared. Okay. So basically this is telling us is we do the integrations over the wall. Okay. And you can see for these special examples, the thickness is pretty much uniform everywhere. So that means the t can be taken out here. So basically, this is simply integration of the whole thing. This integration simply tells us is what is the length of this wall. That's it. Okay, and so for this case, this quantity will be equal to, you can roughly take in the dimension 50 plus 20 plus this one. So for example, this is 30, and plus this one, 30, plus 20, plus 50. Okay, if you're picky, you want to say, can we take the dimension from the middle to middle here? You can do it, but really you can see that compared to that dimension, that really it doesn't matter too much. So in terms of your exercise in homework or for the testing, we just take the easiest one. You simply, based upon the dimension given, just do it. Okay. I don't care about that kind of little discrepancies.
And that's only if it's uniform thickness?
And my solution online for grading is based upon this, the dimensions here.
Did you hear what she said?
That's just for the uniform thickness?
Not for non-uniform, then we can have seen the other example I'm going to present to you.
You have to find thickness in terms of S.
Yes, and I do have the thickness that is different from wall to wall. So we see. Okay, so that one is here. And so again, okay, so now we have a question, how about deal with the thickness that is varying, so I will keep that in mind. So, okay, this is this example here. This example is from our textbook, and so for this example C, we have two types of the cross section. One section looks like this. The thickness is uniform everywhere along the four walls. And for this case, the thickness is thinner on the two sides and thicker on the other two sides. But if you look at the whole thing carefully, the materials made of the sections are the same. Right? They basically redistribute the mass from here to here. Okay. Okay, so for this case, we can exercise their carrying capability. So that is a textbook exercise that we see.